Thank you very much for this very nice talk. And now we have time for questions. So just I'll take Martin. I see your.
Yeah, first of all, thank you very much for your nice talk. You can hear me?
Yes, I do. Yes.
Ah, very good. As you pointed out, the ZT value is a very important figure of merit for applications. Now, I have seen papers that have argued that by using metamaterials, you cannot increase the ZT value with respect to the ingredient materials. Now, what you are telling me here basically is that you can increase the ZT value with respect to the ingredient materials. Can you bring these two things together?
Well, so I will have to see which papers you're referring to, Martin. I assume that the metamaterials referred to there are different than what I presented today. The reason we expect ZT to increase is really as demonstrated in these slides here. If I can get them quickly, it's from a very simple point of view. I would say that we're able to reduce the thermal conductivity using a mechanism that doesn't involve the usual approach of introducing scatterers in the main body of the transport medium. So in this case, the main body is the membrane. That's the membrane that we're starting with. That's the one that we want its thermal conductivity in plane to be very small, while its electrical conductivity and Seebeck coefficient, which I didn't talk about, but these are the two important electrical properties for those to be high. And here we can reduce the thermal conductivity with very little impact on those two other properties, the electrical properties. So from that perspective, we have reason to project an increase in ZT.
Yeah, thanks. As far as I understand, the answer to my question lies in the definition of what they call a metamaterial and what you call a metamaterial, which I guess one can discuss forever. Thank you.
Yeah, thanks.
Thank you. Do you have more questions?
And actually, maybe I should say something very quickly about that. So metamaterial can appear in different contexts. Here, I'm referring to specifically what I call a nanophononic metamaterial, which is basically an atomic scale medium where we're introducing a large number of resonances using intrinsic local resonators. So this is, just for clarity, this is really what I'm referring to here.
If I can just make a comment, I do believe, as Martin said, that everything relies on the definition of the metamaterial. And as you explained in one of the slides, when you start adding like holes or adding some additional scatterers, that would be in the sense that these people predicted, in the sense of metamaterial, that you will start mixing two or many materials together in a bulk fashion. And that in that sense, you cannot increase the ZT. And here everything is on the fact that you have a membrane and you are really adding like an orthogonal contribution to it. And this,
yes,
and this contribution is making the difference to the
indeed. And terminology aside, we can just look at this problem as it is, as you were explaining, Muammar, that we're having this notion of a medium that is free from scatterers. So it can be in principle optimized for electronic properties, but at the same time, we obviously want to reduce the thermal conductivity. So we have an opportunity here to reduce it without using conventional scatterers, by using these extruded substructures, which provide us with local resonances, many of them which reduce the thermal conductivity in the main body itself.
Thank you. I'm just looking at the audience if anyone is raising his hand, or just feel free to ask questions in the chat, or just come to me. If there is no question, I have Erika?
Yeah, can you hear me?
Yes.
So
Yes,
I enjoyed the talk very much. I definitely come more from the mechanics of materials, and so learning quite a bit about metamaterials and definitions, etc. As I understand, you're talking about basically fully dense silicon and exploiting geometries to get these properties. Do you see sort of a direction of getting sort of coupling, using sort of hybrid approach to coupling the sort of subtractive, increasing porosity and playing around with length scales in sort of these mesoporous silicon membranes with this sort of additive approach and changing geometries, being able to get, say, anisotropy in the properties? And where do you see that sort of the potential is?
This is actually an excellent question, Erica. Indeed, we can. And the reason is because we have to distinguish between the two components shown here. So the membrane is the transport component, and the pillar, and this is in a unit cell picture, of course, the pillars are repeated. The pillar is an agent that is its sole purpose is to generate these vibrons, these local resonances, and which indirectly reduce the thermal transport. So we can, in principle, include holes in the membrane, like shown on the left, which would contribute to added scattering, as long, of course, it depends on our interest. If we're still interested in thermoelectrics, and we want to make sure that the electrons are not impeded or scattered, then these holes should be really small and spaced, so that still the electrons can pass through. So we get an additive effect by optimization, just as much and as small and holes as needed to achieve further reduction in the thermal conductivity without affecting the electric properties. But definitely it's additive because the pillar serves a different purpose than the membrane. And this is why, that's one of the reasons we refer to the phonons in the pillar as vibrons, because they really have a very different nature and purpose.
Thank you. Do we have more questions? If not, I have two very short questions. So the first one is regarding the way you compute the dispersion relation in such material. And in particular, in some cases, you had the membranes with, if I remember, 3 or 4 layers of atoms. And then you had on top of it, for example, I think it's another, slides below. You were basically showing just few unit cells. It was very small.
So you're referring to slide 14, perhaps, or which slide?
Yeah, for example, I don't see it.
This one?
Yeah. Yeah. For example, so in that case, okay, you are applying probably some block conditions along the x-y directions, and I'm wondering, that's exactly.
Yes, I think I can explain it perhaps in this slide. Yes, indeed. Yeah. So to answer your question, the first thing we need to do is create our atomic scale model using some chosen interatomic potential, for example, Kirchhoff or Stillinger-Weber, and then we apply block boundary conditions like we do with acoustic metamaterials. So in the case of a membrane, we have to apply it in plane and leave the upper and lower surfaces free. In the case of bulk, we apply the block conditions in all 3 directions, and we sweep the wave vector space and calculate the frequencies by solving an eigenvalue problem. So very similar in that sense. And in fact, in this context, it's usually called lattice dynamics.
And in that case, your variable is the displacement field of the.
Sorry?
Your variable that you have solved the problem for the displacement field.
Yeah, indeed. These phonons, this is a phonon band structure. So this dispersion diagram is for modes of displacement.
Okay, but the atoms, are they allowed to rotate as well?
No, the atoms have 3 degrees of freedom, X, Y, Z.
Okay.
Yeah, because each atom is like think of masses and springs. But of course, the network of springs is much more complicated than a simple mass spring system.
Okay, fine. And then in one of this animation, I saw like 2 atoms almost leaving so that's just the resonance.
Yeah. So this is this is obtained from MD, molecular dynamics simulations. So molecular dynamics simulations, it's often possible for an atom to run off because it's a stochastic process, and this is not uncommon. And as long as you don't get a lot of atoms running off, that should be fine.
Okay, but this is not like the resonance of a particular resonance of that pillar. It's just like a
no. This is a resonance. So this is so actually I should maybe take back what I said earlier. When we're doing MD simulations, we get this notion of atoms running off. Here, actually, this is a mode shape that we obtained by block analysis directly. So we look at this particular point in the band structure and plot the mode shape, and that's what we see here.
Thanks. And the second question is related to that. It looks for me that you are showing also some experimental results. And how do you measure that at so high frequencies?
Yeah, so this is not a measurement based on frequencies. This is Raman thermometry. So it's an established technique based on laser concepts, and there's a few other techniques as well. And this is not an easy task to measure thermal. Remember, there we're measuring the thermal conductivity, so we're not necessarily probing the band structure. It's very hard to do that given the large population of modes and so on. But we're interested in just the net thermal conductivity. So we introduce a laser which has a certain amount of heat and measure the reflected signals and post-process it to predict the thermal conductivity through the dissipation rates and so on.
Okay, thanks for the explanation. Do we have more questions from the audience?
I have some
crazy, Sebastian?
Crazy question. You know that some people look at resonances of trees on substrates.
Yes, including someone I know.
And your dispersion curves are really akin to what we've seen for rods, flexural resonances of rods on a substrate. And we have some homogenized model that gives these kinds of dispersion curves, well, in a, let's say, asymptotic manner. And I guess that these models would apply to your dispersion curves. So perhaps these kinds of models which were designed for forest of trees could be of interest for you in your nanophononic world.
So of course, these are extremely different, probably the most extreme scales on both ends. I would say, doing something like this, Sebastian, like resorting to a continuum model and doing asymptotics and homogenization might be useful in providing some insights onto how a particular pillar or nano resonator influences the local resonance, especially in the long wave regime. But as far as calculations are concerned, we really, as I was saying earlier, we essentially have to resort to atomic description, because the details of these very, very rich and complex phonon band structures are critical for determining the final quantity of K, the thermal conductivity.
Of course. That would be really a partial, inspection of your problem.
To provide some insights, yes.
And I find the fact that you go from the nanoscale to the geophysics scale, quite interesting.
Yeah, definitely. I mean, these are the two extremes, as we say, from a few hertz to tens of terahertz.
Yeah, and there was this Nature paper by Moldovan. He was also so Moldovan also published some papers, in some kinds of. There is this Fish-Revletter paper on this kind of defect states for phonons and so on in some kind of phononic crystal. And what you're doing is. I find this really interesting, because we could also, I guess, adopt a totally different, let's say, stochastic homogenization point of view when it comes to smart transport model and so on, and perhaps there is.
I think so. That'll be interesting to do as well, for sure.
Yeah, yeah, I think you really open new avenues. I mean, these results are really nice, and I particularly like the fact that you kind of mix your knowledge of elasticity and you use it for a very different field. Yeah, fantastic. I discover I don't know at all these kinds of physics, and really interesting. Really well done. Really, I love to see my trees at the nanoscale.
We should talk more then, Sebastian.
Thanks, Sebastian. Do we have a...
Of course, what is very interesting is the trees themselves. They have a structure inside. We can see the atomic structure, and how could we encompass this kind of homogenization for the atomistic scale into the continuum model, which has been already studied before. But of course, this would bring richer physics if this kind of two-step homogenization. First, you would start from the atomic scale, and then you would replace your rod by a continuous effective model, but deduced from the nanoscale. And then you would use what we know from the geophysics scale to skip a step. I mean, it's I'm very confused, but I'm confusing it. It's just that I'm really excited.
I mean, no, for sure. I mean, I think homogenization does have some place in this topic. Not maybe not directly to predict properties, but just to get insights, as you say, for sure.
Thanks. Do we have a, let's say, last question from the audience?
If I can just add to that conversation, because I always find it very interesting how we can exploit length scales in a variety of ways. And really, it's not just looking at the atomic scale and then looking at the tree scale, right? I mean, we know that the trees have this very interesting structure. It's heterogeneous, but it also has sort of a repetitive structure, but with lots of defects. When I think of a lot of the sort of phononic issues, having something that is very regular, right? Acoustic metamaterials and having this very periodic structure, and trying to think about how the defects at what scale can either be exploited or one thing I was thinking about, and again, I will clearly show myself as a non-physicist, are there ways in which one can find these things in colloidal crystals where we end up having length scales that are a little bit more handleable, not to the scale of trees, but something where we can go beyond 10 nanometer sort of limited structures? I don't know if the question makes any sense, and it was probably more of a comment than anything else.
No, I mean, I appreciate these comments. It is intriguing, of course, to compare with the classic, what I would refer to as the classical metamaterial point of view for acoustics and electromagnetics, where we're looking at, as I said, just typically a few resonances in the long wave regime and doing homogenization techniques, looking at effective properties and so on. It's really a very different perspective here, and I tried hard to show the similarities and the contrasts. But at the end of the day, we're working with local resonances, and I think the comments that Sebastian made and you're making are still very interesting, because there's always room to employ different analysis techniques to get insights into the nature of local resonances. I'm showing a slide here, maybe that may add a little to the discussion, especially when we're talking about trees, Sebastian. So we were intrigued and thought, okay, what if we compare having 4 pillars in the unit cell with different heights, so we get different resonances or different sets of resonances, to one pillar that has the same total volume as the 4. So we're comparing apples with apples, except 4 pillars versus 1. So maybe in conventional acoustic metamaterials, there's implications that would suggest that the left-hand side case is better. But as far as this context of thermal transport and our interest in maximizing the conformity between the phonons and vibrants, we actually find that the right-hand case is better. So when we have a large pillar, we get better conformity. So at the bottom here, we're showing the conformity and the density of states between the pillar resonances and the membrane. And as I said, as I explained earlier, we want to increase this conformity so that we increase the underlying mechanisms that contribute to the reduction in the thermal conductivity. And we found here that one large pillar actually exhibits a better set of density of states, and that's because it's more natural when we compare one big pillar to the base membrane. They're more similar to each other, and hence, but one acts as a transport media, the membrane, and the other acts as a local resonating unit. But they're still more similar in some aspect when we have a large pillar, and that's better. So I just wanted to show this to demonstrate that depending on your application and your perspective, you can have different results and different conclusions.
Great, thank you so much.
Thank you. So we have some more questions.
Could I ask a question about making a perfect thermal insulator with a resonant structure? Is it possible? For example, in continuum acoustics, you can make structures like this one I'm holding now, which don't transmit any sound in any mode whatsoever in a certain band, because it's a local resonator with a lot of different resonances, torsional, flexural, longitudinal, etc. Actually, I'm just promoting my own metamaterial, but I thought if you made this atomic scale and you tapered it or something, you could make a thermal insulator. Have you ever thought about making it totally forbidding all possible vibrations?
So that's a really good question. There is a fundamental difficulty in doing that, and that goes back again to what I was showing earlier, which is the very nature of thermal conductivity. If we use this as our measure of thermal transport, unlike acoustics, it's really an extremely collective phenomena. Pretty much all modes in the spectrum. Of course, usually there's a distribution on the importance of the modes as we look through the spectrum. But in principle, all modes, especially for relatively small sizes, where the mean free path on average is quite large compared to the characteristic length scales, typically all modes, if not most modes, we're talking millions of, I might even say billions at some cases of these branches contributing. So I noticed, Oliver, when you were describing your concept, you said in a certain band. So that statement here cannot apply here. So we can, of course, in a certain band, and we showed it here, we can show complete silence and complete thermal insulation. But in principle, that won't work in terms of completely reducing the thermal transport across the whole spectrum. Now, having said that, because of these size effects that I explained, we were able to show extremely strong reduction. So again, I invite you to look at these results very carefully. A membrane, bulk silicon has a thermal conductivity of roughly 140 watts per meter Kelvin. A membrane will have roughly 1/3 or 1/5 of that. An MPM will have roughly 400 times lower than that. So it's in many aspects, you can view this as a thermal insulator because of this very strong reduction. But it's not a perfect. It will never be a perfect thermal insulator.
Okay, thank you. Great answer. So it really begs another question: is what is the theoretical lowest possible thermal conductance of a given element for a given geometry?
That's an excellent question. It might be hard to theoretically derive such a condition or a limiting case, because you would really need to explore many. Again, this takes us to the curse of nonlinearity. Condensed matter physics, by nature, is a highly nonlinear field. As we enter into the realm of actually predicting the thermal conductivity, we need to do simulations, and we need to incorporate the nonlinearity. So it's obviously hard to make any analytical predictions in a highly nonlinear system, let alone nonlinearities between tens of thousands of atoms. So it's really hard to make these type of predictions. However, I can say that as you increase the ratio or the volume of the pillar compared to the membrane, the more you increase that ratio, the more the reduction, up to there's a limit, of course. The limit is when the entire system, when the entire unit cell starts approaching the edges of the distribution of the phonon mean free path at the temperature of interest. Because once you cross that edge, then that takes us to this picture here that I showed you earlier, which basically will suggest that you're no longer a nano system. You're gradually approaching a bulk system where all these concepts are invalid any longer.
I think the question wasn't a good one, because I should have said a given thermal conductivity divided by a given stiffness or something, because you can always make a single line of atoms or something crazy like that.
If you go down
that's
to
not a fair question.
If you go down to an extremely simple case like that, where you just have a line of atoms, then perhaps you can make some of these prediction along these lines. More precise.
Have you ever tried to reduce your problem like that to something?
No, that's actually a good thought. It's a good thought, but again, thermal transport tends to be a problem that is very hard to idealize because of its nature, unlike acoustics perhaps. So usually we don't think along these lines, but I do appreciate the thought. I think it triggered something now in my mind, and maybe one can examine limiting cases as you're suggesting.
Okay, thanks.
Thank you, Oliver. Do we have more questions? Let me ask you a last question before leaving you. In the beginning, we discussed this homogenization problem. And my question is, we had some talks a few years ago regarding the decoupling of the electrical properties from the phononic properties. And the question is, when you go to very small scales, you have, let's call it like two different mean paths, one for the electron contribution and one for the phonons. If now we start laminating, by laminating, I mean just making laminate layers, and we look at different directions of propagation, for example, the electrical or the phonon propagation in different directions. Can you play on this mean path length to make it fully is insulating for electrons or insulating for phonons in a totally decoupling way?
Yeah, so this is I have to say this is a very deep question, because you're asking about the implications of confinement, of going from bulk to let's say thin films or membranes on both the phonon transport and the electronic transport. Both have been explored in the literature. Both are still open to more understanding. From a phonon perspective, the dispersion's flattened just simply by reducing the dimension without even adding any holes or pillars, as I've showed you here. And that one, to some extent, we can, so I'm referring to the middle picture here, we can have some good understanding. On the electronic side, it's an analogous discipline. You also calculate electronic band structure. You can also use a corresponding version of the Boltzmann transport model, but for electrical conductivity rather than thermal conductivity. But there, you most probably you will have to resort to ab initio calculations, which are much more challenging. Not very. It won't be very helpful if you use empirical type models. But when you reduce the thickness, you will get changes in both the electronic structure and the electronic transport environment, the scattering environment, and you'll get very intriguing properties there as well. So you have that opportunity, but the challenge is that usually when you reduce dimensionality, both phonons and electrons will be changed in a similar way to some extent.
Okay.
What we want is we want them to change in a different way. That's the challenge, and that's why this MPM concept and specifically that configuration of pillared membranes can provide an opportunity.
Okay, thanks.
Keep in mind that MPMs is a concept. It doesn't have to be realized as a pillared membrane. I've showed a few papers from the literature that shows other ideas, right?
Yeah.
As these, yeah.
Okay, thank you very much.
It's my pleasure.
So no more question. If there is no more question, let's thank our speaker again. It was a very nice talk. So
thank you so much.
Thank you for giving the talk and answering to all the questions, and thank you for everyone for participating to the MetaMAT seminars.
Excellent. Thanks again.
Thank you very much.
See you all soon.
See you soon. Yeah.
In person.
Indeed, hopefully, in London or Boulder, or anywhere else.
Or Texas or Florida.
Indeed.
Or Marrakesh.
Or Marrakesh. Indeed, Phononics, the next Phononics conference.
Yeah, which hopefully will be held next year. Okay,
That's
great.
true. That's true. Great. Thank you. Thanks again.